Module 8 regarding MPI IO. Okay, in this module, we have a couple of subtopics under this module. First, introduction, concept of IO, next one. After that, function available in MPI IO. And then MPI IO example and performance consideration, okay? Because normally we use MPI to evaluate, or maybe for the performance and so on, yeah. And then collective IO example, some performance tips, common use case, and also exercises for practicing. So means some example regarding or related to this parallel file or parallel IO, yeah. Okay. All right, next. So introduction. So what is MPI IO? Okay. A part of MPI standard, which is MPI 2 or later, that allows processes in an MPI program to perform IO operation in parallel. Okay, it also provides efficient access to files using collective or independent IO. So what is the collective and also independent IO? So both are the primary method, that a processor used to read and write data to share a storage system. The core difference, comes down to the coordination. For example, for independent IO, it is a free for all, while for collective IO is a synchronized team efforts. So in other words, to explain about this kind of the two methods, So imagine, try to imagine classroom of 50 students who all need to hand in a one-page assignment. So independent IO, so every student, for example, if independent IO, so the analogy is every student get up individually and then walks across the room and drop their page on the teacher desk one by one. Okay, that's independent IO. So and then the door get jams and then people collide and it takes a long time. While for the collective IO, so the student pass their papers to the end of their rows, and one student from each row collects the paper, stacks them neatly, and walk them to the desk in a single trip. Okay, all right. So independent IO. So each processor or MPI process operates completely on its own. It opens the file and then move its own file pointer and read or write data whenever it wants without caring what the other processor are doing. If process 0 needs data, it issue an IO request to the file system. And also if process 1 needs data, a millisecond later, okay, so it issues its own separate request. So mean there is no communication between the processor regarding the storage needs, right? So collective IO. So in collective IO, all processors working on a task must participate in the IO operation at the exact same time. It is a structured multi-step process where processors talk to each other to optimize how data is transferred. It is used also to rely on a technique called two-phase I/O to optimize performance. For the phase one, everyone rushing to the disk. The processor talks to each other over the high-speed network. And then they elect a small number of aggregator nodes and shuffle their data in memory so that it is organized into large continuous block. Then for another phase, which is phase two, only the aggregator nodes write the data to the storage system because the data is now in large, contiguous chunks, and then the parallel file system can write it at maximum hardware speed. Okay, comparison among these methods, which is between independent and also collective I/O. And then for the regarding coordination features, like coordinations, for independent, none, which is none available on that. So each process act alone. But for collective, yes, very high, and all processes must participate. Okay, so in terms of MPI function, so this function is MPI read is belong to IO, independent IO, MPI file reads, MPI file write. But for the collective, you want to call this function, you have to use this function MPI file read all. And also for MPI file read all, that one for collective, And then regarding data efficiency, regarding these features, in independent I/O is often result in tiny, fragmented disk also request, but for the collective, merge requests into large, and it create the contiguous blocks or chunks. All right. And then for the network usage, for the independent I/O, low inter-process communication and also high data traffic. High disk traffic. And for the collective, it will give high inter-process communication and also low disk traffics compared to the independent I/O. So that's regarding network usage, And then for the features, which is the fifth feature, which is best used for, and then for the independent, good for the small, irregular, or localized I/O operation. And for the collective, of course, it's a good for the massive data sets, grids, matrices share across thousands, of course. So if we look into the current or real scenario of this kind of the application, almost the data is very big, huge data. So of course, collective is the best option for that, Okay. But for the small, you can use this independent I/O. All right. So key concept in MPI I/O. So concept file handle, which is concept for the file handle similar to the file pointer used in MPI to refer to an open file. And then for the file view concept, define how each process view the file data, which is it offsets, data type, and also layout. And then for the collective method, all process work together for the I/O. This one I already explained. And for the independent, we use this kind of the function, this one. Okay, each process perform I/O on its own for the independent I/O. So this is key concept in the MPI I/O. All right. And then function overview in MPI I/O. Okay, I already explained also. So for the file operation, like MPI file open, you use this function. And for this, we use it for the close, and so on for the viewing. So we use this for set view file for a process, for example, offset or data type, okay? So writing and reading. So for the independent, we use this function, and also for the collective, we use this kind of the function. All right. Okay. So MPI IO example. I just go to the concept. Yeah. So simple IO, you can use this to generate a simple IO example. Okay. All right. So you can have this code. Okay, very important MPI rank. We already mentioned, and then this the file. We use the which one? The very important. This one for the file write. Okay, and this initialization in here. MPI init here initialization, and then we do setting on that. Okay, and this is the file that we're going to open, and then we do write on the yeah. Okay, this example one. Okay, so I will share this slide later in our e-learning. Yeah. So data may override each other. So fix it using offset. Okay, we use offset to locate all the data, so easy to access that. So this is the instruction or the code that we use offset. Okay, and then each process write a unique location. So we use location, and then there is a unique location, and then which one we use offset concept. So we got MPI offset here to access that. Okay, try to understand this one. Yeah. Okay. And also distributed. Another example, distributed sensor data logging. So scenario, you are working on a distributed monitoring system where multiple sensor. Okay, we can say multiple sensor is like processors here. So collecting of data. So how to manage all this? So try to imagine that not just a single only 1,000. So it's a huge of the data, numbers of the data. Okay, try to collecting, especially in this case, regarding temperature data. Yeah. So each process will generate its own data. So write it to a share file and must avoid overwriting other processes data. So ultimate goal, use MPI IO. So each process write to a different location in the same file. That's why we use that offset. Okay, this is the code. Try to understand that. Okay, so we open and then we do some, this one offset. So here calculate offset, then write data to a specific position. Here, next one, if you, okay, here, and then calculating the result. All right. Okay, and after that you close. When you open, you have to close that. Okay, this is another example. Okay, code. Okay, and then here, this is the instruction to compile, and then this is the expected output. Okay, from that code. And so the final sensor data bin with process write to a unique location with assumption no data corruption. So this is the value, that the location of the data. Okay, all right. And then so that code actually will generate parallel IO, so all process write simultaneously. So we got this MPI offset in the code. So this one locate the location of the data, and then no overwriting without data corruption. So with offset, save parallel writing. So this is normal practice that, okay, we are going to use data, so we use this kind of the offset, yeah, technique. Okay, what happened with the offset? If you replace this with this, okay, so all process will write at the same location, so not overwritten data. Okay, this is what happened if we not apply offset. So extension again here, read data back. So add this after writing. So we use this, all this code. Yeah. Okay. Next. Okay, use collective IO, replace with this. Okay. Parameter at all. Okay, this function we already introduced at the beginning about this function. Use that, and then this will basically we improve performance for the large system. Okay, that's for sure. Yeah. So summary, MPI IO allow parallel file writing, offset, ensure data separation, and essential for the large-scale distributed system. Okay. All right. So another example, student marks recording system. Okay. For project, maybe there could be some final project for this. Okay. More on huge data. So later I will explain about the project. Okay. Example 3, yeah, student marks record system. Okay, scenario, each process represent a lecturer entering student. This one on a small scale, okay? Each process represent a lecturer entering student marks into a share file. So each lecturer must write a separate position to avoid overwriting. Okay, this is the code. Try to understand that, okay? And then next, okay, this is another part of the code. So try to understand. So we use lecture, okay, data of the student, how to want to generate that. Okay, you can use the example to understand about the MPI IO. Yeah. And then another example, parallel log file system. Okay, this scenario, each process represent a server node writing logs into a share file. So instead of binary, we write a text logs with proper spacing. Okay, so this is the code. Yeah, for the parallel log file system. And this the part of the code we can try to run and understand this code. Yeah. So yeah, this one also use a MPI offset. Okay. All right. And then another example, parallel array storage, which is for scientific data. So we talk about scientific data, we can imagine, yeah, the data is not just a million or thousand, it could be more than that. Yeah. So a large data set is divided across processes. So each process writes part of an array into a share file. Okay, this is the code. Okay, try to understand that. This one, we got the offset as well. So need to run and understand this. Yeah. So this is the example also. Okay, how we want to, because the file here, because maybe I will not provide, but you can create based on the file, the parameter. Yeah. Okay, just create something that try to understand and create the dummy. Okay, I don't provide you all this, yeah, because here just the lecture on the concept of the MPI IO. Yeah. Okay. Maybe in the lab activity there is some example. Okay, the code that you need to run. Okay. All right. Okay, and then next for performance consideration. So normally, okay, when we use the MPI, of course, they will check the performance, how good. The basically is already proved that for the massive data or massive application, we're going to use this what you call collective IO, okay, because of the performance. Okay, factor affecting the MPI IO performance. One of the factor, maybe some research also, we found that still there is some need to do some improvement on the, for example, here, disk space, file system, number of processes, access pattern also, sequential versus random also. So this also will affect the performance of the MPI IO. Okay, this one come from the research because I will not explain on detail on that. Okay, this is good also. If you're interested on this kind of the parallel programming, especially on this MPI IO, so this is parameter that will affect the performance of MPI IO. Yeah, all right. So best practices, use quality IO when possible, of course, okay, because based on the explanation that I gave to you also, so quality IO is the first priority because if you have a massive data, huge data, yeah. So avoid overlapping writes, align data with file system block and use file system for, and use file views for structured access, all right. And then collective again, so maybe there's some duplication about the example, yeah. Okay, high performance. For this, our processor will write their portion together, synchronize and optimize MPI IO. So I told you this one because I just modified this slide. So I put on some extra explanation regarding this, but otherwise you not understand. So that's why I give at the beginning, you see all the codes, yeah, all the source code regarding collective IO, yeah. So this is only portion, only the function itself, okay, not the the code which include all these function, yeah. So this is the collective IO. So scenario, all process cooperate to write data using collective IO. Okay, so this is same thing that I want to explain. So this one of the example of the code, yeah. And also this, we got offset. Okay, and then yeah, file and then collective B we don't have, but this we normally use that. We open the file, yeah. Okay, and then we try to process that, yeah. Okay, so then performance tips. Next one. So that's regarding the just now regarding MPI. So now performance tips. So use collective IO for when possible. Set file view smartly to reduce sync and loop overhead, and prefer large contiguous write. Okay, that's regarding all this performance on this MPI IO. And for the common use case, writing data, large data set in scientific simulation and distributed logging or result, and also checkpoint on parallel. Okay, so basically all this is good for the parallel, yeah, parallel. Right. Okay, and also implement collective, right, MPI, and then also for some create file view where process skip some bytes, yeah, writes. Skip some byte between writes, for example, for interleave layout. All right. Okay, that's all for MPI IO for this chapter. All right. Thank you for listening. Bye-bye.